Every day, we operate on a basic set of assumptions. The floor is solid, the past is fixed, an object can only be in one place at one time. These aren't just ideas, they feel like undeniable facts about the world. But what happens when science pushes the universe to its absolute limits, to the searing edge of a black hole or the quantum realm of a single particle? Physicists have discovered places where the very logic of reality breaks down, revealing a foundation far stranger and more mysterious than anything we've known. 1. Different rules in different places. Our first paradox is based on one of the fundamental constants of nature, is the fine structure constant, known as alpha. This number, about 1/137th, sets the strength of the electromagnetic force. It governs how electrons bind to atoms and how light interacts with matter. If alpha were even slightly different, the universe we know could not exist. For decades, we assumed alpha was truly constant. But in the late 1990s, astronomers began using light from distant quasars, beacons from billions of years ago, to check. The light passed through ancient gas clouds before reaching Earth, imprinting spectral fingerprints that could reveal whether alpha had the same value back then. Between 1999 and 2010, some of these measurements, taken with telescopes in Hawaii and Chile, whispered of something astonishing, a tiny but systematic change in alpha across the sky. By 2010, one analysis claimed a dipole variation, meaning alpha might be slightly stronger in one direction of the universe and weaker in another. This was more than a crack in our understanding. It hinted that the laws of physics themselves might not be universal. If true, it was a glitch of cosmic proportions. For the next decade, the anomaly lingered like a ghost in the data. Some reanalyses confirmed it, others dismissed it. Everyone agreed the old spectrographs had limitations, tiny calibration errors that could mimic the effect. But until a purpose-built instrument could weigh in, the question remained unresolved. 2. A strange pattern in the sky. The cosmic microwave background is the oldest light in existence. Described as the afterglow of the Big Bang, it shows us a perfect snapshot of the universe merely 380,000 years after its birth. Theoretically, this picture should be almost perfectly random, a messy splash of tiny hot and cold spots. And for the most part, it is. But when scientists looked closer at the most prominent features in the image, they found patterns that shouldn't be there. On the grandest scales, the hot and cold spots align in strange, orderly ways, creating what some astronomers have dubbed an axis of evil. And most suspiciously, this cosmic axis seems to point in a particular direction, one that roughly aligns with the plane of our own solar system. It's a deeply uncomfortable hint that we might be in a special place in the universe, the very idea science has spent centuries trying to disprove. But physicists are skeptical, and rightly so. It's incredibly easy to find patterns in random noise if you look for them. As the saying goes, if you shoot 100 arrows at a barn door and then draw a bullseye around one, it doesn't make you a master archer. Scientists worry they might be doing the same thing here, finding the one strange feature in a single snapshot of the sky and giving it too much meaning. These anomalies could also be a kind of mirage, a trick of the light caused by dust in our galaxy, or even tiny systematic errors in our incredibly sensitive telescopes. For now, the axis of evil remains a compelling cosmic mystery. It is most likely a statistical fluke or a smudge on the lens, a glitch in our map rather than a glitch in the cosmos. But it serves as a potent reminder that science must always guard against its own desire to find significance in the static. 3. The universe's data leak. Physics is built on one sacred rule: information can never be destroyed. This principle, called unitarity, ensures that the universe has a memory. Every event, every particle, every interaction leaves an indelible trace. Hence, the past is never truly gone. But in the 1970s, Stephen Hawking made a discovery that threatened to shatter this rule. Black holes, the universe's most perfect prisons, actually leak. Over immense timescales, they emit a faint glow called Hawking radiation, causing them to evaporate into nothing slowly. But it wasn't just this slow disappearance that concerned scientists. According to Hawking's calculations, this radiation was random, carrying no trace of what the black hole had swallowed. A star, with all its complex information, could collapse, the black hole could evaporate, and all of that information would simply vanish. It was as if the universe's memory could be wiped clean. This fundamental conflict between Einstein's theory of gravity and the laws of quantum mechanics is known as the black hole information paradox. Decades later, in 2012, this troubling inconsistency became a full-blown crisis. A new thought experiment revealed that if information did somehow escape, it would require, at the black hole's edge, a violent curtain of energy so large that it would instantly incinerate anything trying to enter. Physicists were trapped. Either information was lost, breaking quantum mechanics, or a firewall existed, breaking Einstein's theory of gravity. It seemed as if the laws of physics themselves had broken down. For a time, the paradox seemed unbeatable. But then, faint clues to a resolution began to appear. In 2016, a team including Stephen Hawking himself proposed that black holes might be adorned with what they called soft hair. Not literal hair, but a kind of quantum memory etched into the event horizon itself, subtly encoding information about its past. It was an elegant solution, but still far from a definitive answer. The real breakthrough came in 2019. Theorists discovered a stunning new piece of mathematics they had overlooked: strange connections in space-time called replica wormholes. When they included these wormholes in their calculations, everything changed. They revealed that the information isn't lost at all. Instead, it gets mirrored onto a section of the black hole's interior, called an island. Through the bizarre logic of these wormholes, this island is simultaneously inside the black hole and part of the radiation outside. It's as if the universe makes a hidden backup copy. As the black hole evaporates, the information is returned to the cosmos not directly, but through its deep quantum connection to this island. This new insight doesn't just solve a paradox, it challenges the very nature of space and time. It suggests the inside and outside of a black hole are not what they seem, but are linked by hidden passages through a deeper layer of reality. This solution forces a disturbing trade-off. Perhaps the data leak is an illusion, but only because space-time itself is. The original glitch, then, may not have been the true problem, but a warning. A single loose thread hinting that the entire tapestry of reality is woven in a way we can barely comprehend. 4. Instant links across space. Imagine two coins, linked by some invisible thread. You give one to a friend who travels to the other side of the galaxy. You flip your coin, and it lands on heads. Instantly, you know your friend's coin will land on tails. This is the essence of quantum entanglement, one of the most celebrated and misunderstood phenomena in all of physics. When two quantum particles are entangled, their fates are intertwined, no matter how far apart they are. A single shared wave function describes them. Measuring a property of one particle, such as its spin, instantaneously influences the corresponding property of the other. If you measure one particle's spin to be up, you know with absolute certainty that its partner's spin will be down. Albert Einstein famously derided this as spooky action at a distance. It appeared to violate the cosmic speed limit set by his theory of relativity, which states that nothing, not even information, can travel faster than light. For decades, scientists debated whether this spooky connection was real or just an illusion. Perhaps the particles were like a pair of gloves separated into two boxes. If you open your box and find a left-handed glove, you instantly know the other box contains a right-handed glove. The information was always there, you just revealed it. This idea, known as local hidden variables, suggested that the particles had definite properties all along, hidden from our view. A series of brilliant experiments finally settled this debate in the most astonishing way. Physicists John Bell, Alain Aspect, John Clauser, and Anton Zeilinger devised and executed tests that could distinguish between true quantum spookiness and hidden classical information. Their work, which earned them the 2022 Nobel Prize in Physics, conclusively showed that the hidden variable's interpretation is wrong. The universe is genuinely non-local. The correlations are real and are established faster than light could travel between the particles. These experiments have even closed a bizarre loophole called freedom of choice. The worry was this: what if the entangled particles in our detectors weren't acting randomly? What if they were secretly coordinating based on some unknown event in their shared past, creating a fake correlation that only looked like spooky action? To eliminate this possibility, scientists needed a truly random signal to decide their measurements, one that could not possibly have coordinated with their lab equipment in advance. So they looked to the heavens. In cosmic bell tests, They use light from ancient distant quasars as their random number generator. For example, the color of a photon arriving from a quasar billions of light years away is used to pick a measurement setting here on Earth. Since that light was emitted long before our planet even existed, there is no way it could have been part of some grand, predetermined plan involving the particles in the lab. It is the most random and independent signal imaginable. And the result? Even with the measurement choices being set by light from the dawn of time, the spooky correlations between the particles persist. This is the ultimate loophole, a violation of the universe's most basic rules. But there's a crucial catch. While the correlation is instantaneous, it cannot be used to send a message. You can't control the outcome of your measurement. It's random. You might measure up, and you'll know your friend's particle is down, but you have no way of forcing your particle to be up to send a 1 instead of a 0. It's only when you and your friend later compare your lists of random results over a classical communication channel, like a phone call, that you discover the perfect anti-correlation. The no communication theorem ensures that relativity's speed limit remains unbroken. Entanglement is a window into a deeper layer of reality, one that is not constrained by our intuitive notions of space and separation. It reveals that the universe is interconnected in ways we are only beginning to comprehend, a web of non-local relationships that is far stranger and more subtle than any classical construction. 5. Where is everybody? There are more planets in our galaxy than there are people on Earth, which tells us something profound. Worlds are not rare. They are everywhere. The universe is ancient, and the chemical building blocks for life are abundant. Logically, the cosmos should be a noisy place, teeming with civilizations. And yet, the output is nothing. A profound, unnerving silence. This is the Fermi paradox, and it feels like a fundamental glitch in the universe's system. All the components for a vibrant, populated cosmos are present, but the program isn't running. This silence is so complete that it forces us to look for a bug in the system. Is there some hidden rule, a great filter, that inevitably terminates complex life? Are we living in a cosmic zoo, deliberately isolated? These dramatic explanations are attempts to account for the unnerving emptiness. But the true nature of the glitch may be revealed in the scale of our search and the uncertainties of time. Our loudest shout into the void has created a radio bubble only 120 light-years across in a galaxy that spans 100,000. It's like checking a single pixel on a vast, dark screen. Even if life is common, the famous Drake equation reveals the real problem: the universe's operating parameters. The distances are too vast, and the lifespan of a typical civilization might be just a few thousand years, a mere flash of light in the great dark. When you consider this, the silence stops being a paradox and starts looking like a feature of the glitch itself. 6. The universe only solidifies when you look. At the quantum level, reality is a haze of pure potential. A particle, like an electron, doesn't commit to a single location. Instead, it exists in a superposition, a ghostly cloud of all its possible positions at once. This cloud, known as the wave function, is perfectly well behaved. It evolves with clockwork predictability, following the elegant rules of the Schrödinger equation. But then, the moment a measurement is made, this elegant evolution shatters. The cloud of possibilities instantly collapses into a single, definite outcome. The electron appears at one specific point. This sudden, violent transition from a haze of potential to a single concrete reality is the measurement problem. Why does the act of observation, of measurement, hold such a special, decisive role? What is it about looking at a system that forces the universe to pick one reality out of an infinity of possibilities? This reveals a kind of schizophrenia in the laws of physics. On one hand, you have the wave function evolving with perfect clockwork order. On the other, you have the violent, random collapse the moment a measurement is made. The central mystery, one of the deepest in all of science, is how to reconcile these two opposing rules without resorting to the magic of a conscious observer. This apparent glitch in reality's core logic has led to a century of debate and a host of competing explanations. The most practical explanation is decoherence. This idea points out that no quantum system is ever truly isolated. It is constantly interacting with its surrounding environment, a chaotic bath of air molecules, photons, and thermal vibrations. These countless tiny interactions effectively measure the system constantly. entangling it with the broader world. This entanglement rapidly suppresses the weird quantum interference effects, making the system behave classically. Decoherence explains why macroscopic objects, like a cat or a planet, are never seen in a superposition. They are too big and too messy to remain quantumly pure. While this theory does explain why the world appears classical, it doesn't solve the core problem. Why do we experience only one of the many possible outcomes? This leads to a more radical proposal, the many worlds interpretation. First proposed by Hugh Everett, this view argues that there is no collapse, ever. The Schrödinger equation is the only rule. When you measure a quantum system, the universe itself splits. In one branch, you measure one outcome. In another, parallel branch, a copy of you measures the other outcome. Every quantum measurement creates a cascade of new universes, a branching multiverse where every possibility becomes real somewhere. There is no glitch. The laws run perfectly, building an ever-expanding tree of realities. We only perceive one path through this tree. On the other hand, some views like quantum Bayesianism or cubism reframe the question entirely. They suggest that the wave function isn't a real physical object at all. It is simply a mathematical tool that represents an observer's knowledge or belief about a system. The collapse is not a physical process happening in the world, but a sudden update of information in the mind of the agent making the measurement. Reality doesn't take form because you look. Your understanding of it simply sharpens. The measurement problem remains unsolved. It's a profound glitch that forces us to question the relationship between the observer and the observed. Is reality a fixed stage, or is it a participatory drama that only solidifies when we play our part? 7. The future rewrites the past. The most mind-bending glitch in the quantum world is an experiment known as the delayed choice quantum eraser. It takes the famous double-slit experiment, where single particles create an interference pattern as if they pass through both slits at once, and adds a terrifying twist that involves rewriting history. In a modern version of this experiment, a particle, say a photon, is sent towards a double slit. The outcome hinges on a central rule of the quantum world. If you have no way of knowing which slit the photon went through, it behaves like a wave, creating a beautiful interference pattern of stripes. But the moment you gain which path information, the moment you know which slit it took, it behaves like a particle, and the pattern vanishes into two simple bands. This experiment is cleverly designed to gain that information using entanglement. The first photon is entangled with a partner photon that travels in a different direction. By measuring this partner, you can learn which path the first photon took, and the instant you do, you force it to act like a particle, destroying the interference pattern. But here is the twist. The choice of whether to measure the second photon, and thus gain the which path information, is made after the first photon has already hit the detector screen. This should be impossible. It's as if the universe's event logs are being edited in real time by the future. But the explanation for this temporal paradox reveals a far deeper and more unsettling glitch. The magic isn't that the past is rewritten, but that the past seems to wait to be written at all. By itself, the raw data from the first photon's detector is just a meaningless, washed-out pattern. The magic happens only when you sort that data using the information from the later measurement of the second photon. Think of it like a pile of confetti on the floor. Only when you decide later to sort it by color does a hidden picture emerge. The glitch is that the universe seems to know what that hidden picture will be, holding all possibilities in suspension. No message is sent back in time, and no history is actively overwritten. But this is where the true glitch lies. The universe doesn't seem to commit to a single, concrete history until all the information is in. A photon hits the screen, but its story, whether it traveled as a lonely particle or an interfering wave, remains an unwritten draft. The universe keeps its own log files open, waiting for a future choice to determine how the past should be read. The glitch isn't a violation of causality, but the unnerving realization that reality itself might be a story that only gets finalized in the telling. The rules are not glitched, they're alien. So after this journey to the edges of reality, what is the verdict? Is the universe broken? Perhaps that's the wrong question. What if these glitches aren't errors, but features? Each paradox, from a black hole that seems to erase the past to a future that seems to write it, could be a glimpse of a deeper layer of reality. Fundamental cracks in the surface of the world, pointing to a different set of rules operating underneath. The true mystery, then, isn't chaos, it's consistency. A ruthless consistency in the universe's strangeness. It is non-local, yet it follows rules. It is probabilistic, yet it builds our concrete world. It is the logic not of a familiar machine, but of something profoundly alien. And that may be the deepest truth of all. We don't need to invent an external architect for these mysteries. The real horror and the real beauty is confronting how utterly alien the rules themselves have been all along.